So I'm going to be talking today about a visualization system called Sparkle, and more importantly, some of the lessons we've learned while building it. So my name is Lee Migdal. I'm currently employed at Nest and Google and have some affiliation with TypeSafe, and I've worked at a bunch of other places, but the things you're going to hear today are my own opinions. I'm sure many of my colleagues, some of them still in the room, will disagree with me. The talk is divided into 3 sections. First, I'll give you an introduction to Sparkle, and then I'm going to do a dive into 2 areas that I think will be of broader interest. One is about performance and scaling, particularly around the use of streams. And then I'm going to talk a little bit about architecture, particularly about the Lambda architecture. And with luck, I'll throw in a few demos, a couple at the beginning and a couple more at the end. So what is Sparkle? Sparkle had its origins in an engineer's tool for doing data visualization. I was working on performance analytics, trying to make sure our Nest service didn't fall over under load, which is, of course, a very good problem that one could have to worry about, and wanted an easy way to do custom visualizations. But since that time, Sparkle has been growing up and is becoming more and more of a platform for building custom visualizations that can handle much larger data sets. Sparkle is open source. It's Apache 2 licensed, and you're welcome to take a peek at it over there on GitHub. Wait a couple of days after the conference and I'll have even these latest demos pushed to the repository. So it's a set of modules for building a data pipeline designed for visualization. It includes some loaders, so you can, in the desktop case, load some stuff from a file sitting on your disk, and in a larger scale case, load from perhaps Kafka or HDFS. It is built around the idea of having a fast storage layer. It's a column-oriented data model and very much built on immutable data. I know for this audience I don't have to talk about the benefits of immutable data. And included even in the open source version is an implementation of the storage API based on Cassandra, and also one that just uses RAM as the storage backend for testing. So then, core is this column store, and then connected to the column store is a computational server that can host light mathematics that one can do on the data pulled out of the store. So aggregation, because there's a lot of time series involved in Sparkle, there's some custom aggregators for time series, but really the idea is that you can extend, plug in your own transformations and do more than the built-in ones. Okay, having loaded and then stored the data and then maybe done some mathematics on it, then we want to deliver that data to clients. And the idea is to there's a proposal in Sparkle for a draft of a standard way to communicate streaming data from a visualization server to a client. It's documented. You can follow that link later. It's designed for streaming. It's JSON based in the first draft to make it convenient for both web clients as well as mobile clients perhaps. And if you're working on a visualization system, I'd encourage you to take a look at that and perhaps talk to me. Maybe we can collaborate on making this protocol something generally useful. Sparkle also includes excuse me, a sample visualization client, kind of a test bed for doing some of the visualizations. It's built on D3, makes it relatively easy to, again, throw together these simple dashboards. And I'll give you a little demo now. So first let me fire up. I'm just going to run from SBT. See, I ran from just upgraded to JDK 8 and haven't updated yet. So I'll launch it, and including the, I passed along this argument saying, well, there's some JavaScript hosted visualizations. This is the particular route, this is the particular dashboard I want to show, and that's going to make this thing turn alive. So let me drop a little data in there. So again, this is that I mentioned there's various ways to load data. So here's a little desktop way. I just dropped in some CSV file. And that will now make hopefully, my demos alive, right? So now the idea here is I could have some pre-made simple JavaScript dashboard so that I'm looking at my performance data from my server cluster, whatever it is, and it'll just pop up with the data. And what's fun, what I'm aiming for is to have this really immersive experience where it's kind of smooth and you can zoom around and drag stuff back and forth, and the back button works, and it's just kind of fun to be able to explore the data. And of course you can have multiple axes, right? And what else do I have here? Oh, and multiple, if you're going to build a dashboard, you're going to have two of these things, and I'm going to zoom at once. Okay, so the idea is we're going to be able to build these things really easily. In fact, here, that first chart here is basically the code to create it, right? It's a little bit of fairly declarative JavaScript. There's not much there. The framework does all the work for you. And I have one more thing I want to show you here. So those ones I just showed you were kind of pre-made, and this one is a sort of generic, not a generic dashboard. I showed you dropping some things in, but I wanted to point out a little bit about why it's interesting to do some of the visualization transformations on the server side and not the client side. So here I've uploaded another file which is the same data, just a little bit more of it. Okay, so we sort of see those same spikes. And again, I want to have this kind of nice zoomy, I don't know if you can see it, but when you get to play with it, right, you get to zoom around, you want to explore the data, you want that feeling. Okay, so here, let me make this a little more obvious. And here, this is also just showing some of the things you can customize in the underlying graphics layer. This uses D3, it's very flexible. Here, let's make this orange, because okay, so the aggregation, now this is picking which of the built-in transforms we're going to be running on the server side. Let's see if I can. So, so this is, even with the triple size data, is reasonably zoomy and interactive. I guess, can you guys sort of see how it's zooming around? So I'm going to turn off the aggregation on the server side. I have to make that a little smaller. I'm going to set that to raw, which means stop running the transformation on the server side. Okay, and now if I drag and let go, it kind of gives that ka-chunk thing, right? It didn't really zoom. I mean, it changed, but you kind of lost the fluidity. Right, and the difference is, again, by doing what I'm doing here is I'm just sending, this is really just 3 times as many points. It's not that much data, but it's enough to start clogging the browser. So even with this small data set, you can start to see that it is worth doing transformations on the server side, aside from the fact that the server is much more, a much happier place to write transformational code. Okay, so that's kind of the basic overview of Sparkle, right? A set of pipeline stages. I demonstrated here running locally on my laptop how we could do this in the small, but this was running a Cassandra backend sitting here on my laptop. And it's really the same pieces that we would scale up to run in a larger scenario. Okay, so with that background, now I want to talk a little bit in this second phase of the talk about performance. And the punchline in performance is if you're building a data pipeline, a data system, and you want it to scale and be performant, what I think you ought to use is asynchronous streams of arrays as your core data type. But let's get there. So the API I'm going to talk about is the API where we're getting the data off of the database, off the disk, and over to the transformational engine. And you might imagine, it's a column store, keys and values, time value typically. You might model that as a standard Scala collection of these values, of these essentially tuples, right? But of course, we're going to look at performance. We want to keep this low latency feeling as we scale the system up and handle more and more load. And how are we going to do that? Well, there's a lot of ways to do performance, but here is my 4-step approach to doing performance. So first, what I do is I'd add direct measurements right in the code. Right? What I want to do is I want to see right next to the code that I hopefully understand, how the performance is going to work in the sort of single stream, the single column case. And of course, I got to run that test a zillion times to deal with the JVM overheads, right? But I'm gonna measure the end-to-end time and the time of the major components in my code. And if my code is executing in some asynchronous framework that has mysterious thread scheduling going on, that I'm going to put timing blocks in the synchronous portions, the parts that I'm really going to understand, so that I can isolate what the framework is doing versus as a component of the overall time. Okay, so then once I have that kind of base understanding, then I'm going to mix that with what I can see from a CPU sampler. Your kit is probably my favorite of those. And then, and only then, once I have this kind of ground understanding of the single performance, then you go and add the load, right? And then you measure your throughput and latency if latency matters to you under load. And of course, on the JVM, you're going to very quickly get into wondering about garbage collection, and I would say Sensum is my favorite tool for that. Excuse me. So as soon as we start doing that on this API, what we're going to find is those tiny little tuples are all over the CPU utilization and all over the garbage store. We're going to see a zillion of these little I think I call them events, little of these box keys and box values. And worse, like, these things are not even near each other in memory. They're actually could be spread all over the place. This is terrible for CPU cache performance. So what's the solution to that? Well, of course, the solution to that on the JVM is to go to arrays, right? The JVM provides 8 or 9, primitive type. In the JVM bytecode, there are arrays of primitives. Those are the ways that's the way you get dense, efficient storage on the JVM. Your code can run in tighter loops, so you want to have these tight arrays. So in this case, this two, key value, time value thing, we'll have 2 arrays. They may be of different data types, and we may want to process them separately, but essentially we're going to get down to 3 objects rather than 1 object for every element in for every tuple. So that API might then look something like this, right? We return a data array, this object that points to 2 arrays. Okay, so that's pretty good. If we try that, that's actually going to help a lot. The dense arrays are going to be more efficient, and we're going to use less memory. Are we done? Never give up, right? We're never going to give up that easily. So let's think about latency now. So we said we're going to measure the component timings right? The major components, and so you think about the total time is going to be this sum, you know, in this case, you know, the fetch from the disk plus the math crunch plus the serving time, right? We add all those things up, and that's our total latency. You start thinking about it. Now, I've heard about this reactive stream stuff. You know, if I could just maybe kind of pipe overlap those things a little bit, you know, that might really help reduce my overall latency. Probably not my throughput in this case, but my overall latency. And I think that really is a good reason to go look at reactive streams. But I want to give you another one perhaps not as often discussed. And so I said we're gonna at Scale we're gonna look at latency and also throughput. So you know, throughput, right? We got this pipeline, and then we're gonna try to see how many of these things we can jam onto the machine at the same time. And what's going to slow us down is when we run into some resource contention. Ultimately, you know, hopefully we're going to be so efficient we're going to run out of CPU. But you know, on the way to getting there, we're going to discover that we stumble on not having enough memory, or not having, you know, memory is actually the one that's likely to get us in a high volume. So let's look at memory. Okay, so we got these data arrays, these, you know, kind of big arrays. Each of these arrays, you know, those K's and V's are not to scale. You know, this could be 100,000, 1 million elements in those arrays. Right, and you know, is that going to do well for? We're trying to be low latency. Is that going to work well with you know, with the JVM and garbage collection? Well, you know, when you think about that, the first thing you think about, right, for performance on JVM, right, you got to fit into the generational hypothesis, right? The garbage collectors are designed around this idea that the objects that die are likely to be the young objects, right? This is kind of the basics. And so if you want the JVM to work well, you have to fit into this hypothesis. You know, the garbage collectors, you know, they'll focus all their energy on just these young objects and ignore all the old objects, and that's what makes the garbage collection efficient, right? And that's what they're designed based on that assumption. And if you want to be fast, you're going to need to fit into that assumption. So are we going to fit into that assumption? Our data array is going to fit into that basic, you know, generational hypothesis. And you know, at first blush, it sort of seems like the answer is yes, because we're doing stuff here low latency. I showed you dragging stuff around. So these arrays seem like they're going to die, you know, within a second or two, right? They're not going to last very long. So that seems like it ought to be pretty good. But that analysis is insufficient as you start to look at throughput. And the reason is, you know, we gotta have a lot of these things going on at once, right? And so we have not just, you know, how long does this thing stay alive for, but how many of these things are alive at the same time, and can we fit them all into this new generation that's going to be garbage collected so quickly? And of course, remember, the new generation, well, it's not like all of your heap, right? You know, you got the old generation, that's at least half the heap, right? Probably more. And really, the new generation, you know, it's kind of, you got the Eden, and you got these survivor spaces, and something survives a collection, it's actually got to go in one of these tiny little survivor spaces, so, you know, that's like maybe 1/10 of the heap, you know, if you're lucky, right? So this is, you actually got to fit this stuff into very little space. And what's going to happen is, when you're trying to fit into the generational hypothesis, right, the garbage collector is going to fire into a collection, you know, of these objects that it's hoping are going to be dying young. And what it's going to find are these objects that are, you know, each of these dotted lines or collections, you know, what's still alive, right? What can it throw away, and what does it need to keep? Well, so the live set here is going to be pretty large, and you remember the yellow kind of survivor, it's not going to fit, right? We're going to get this, you know, premature promotion fail. It's, you know, you get all these bad garbage collection words happening. It's not good. Okay, so what's the solution to that? You know, these arrays seem great. We don't want to go back to the tuples. Well, the solution to that is to break up the arrays. So rather than having an array of, you know, 100,000 points, let's have an array of a few thousand, you know, 5,000 points, right? Not 3 here, that's not to scale, but, you know, because that will give us the you know, the major performance gains that we got from arrays. You know, we'll get the 90% gain of the density and the cache efficiency. But then look what happens when, you know, one of these collection attempts happens, right? some of those blocks are done, and some of those blocks don't exist yet. So the actual ones that are live are quite small, and that's going to fit into our new generation quite a bit more comfortably. Okay, so both the latency goal that we started with, but more interestingly, this throughput goal, is going to bring us to something where instead of having one data array for our read request, we're going to have some kind of an asynchronous stream of data arrays. So the lesson here, we decided, we were interested in going reactive, both because it was trendy and we wanted to save latency. And there's a surprising thing that going to reactive streams actually reduces garbage collection pressure. And the key to understanding that is that this transient working set, right, is smaller because of the streaming technology. And really, that's going to be true regardless of how we do the memory management, right? We are reducing the amount of memory we need to have at any one time, whether it's the JVM new generation or some other way. So I hope that's a kind of surprising new benefit for reactive streams for you. Okay, and so we were talking about the API for reading off the database and delivering it, but really this technique of having blocks and asynchronous streams of blocks applies throughout the system, right? I'd recommend doing it in your streaming layer as well. Read off Kafka's pretty fast already, but set the stage for your downstream pieces. In Cassandra, we've seen an order of magnitude improvement, even 2 orders of magnitude improvement by moving to blocks. And extend the streaming idea, not just between the JVM-based servers in your server cluster, but all the way out to your visualization clients, right? That gives you some of the same benefits. And so that's why we have this protocol defined where you send a request up and you get a response back, right, like HTTP, but this is designed to go over something like WebSockets so that we can send, more and more updates, right? So it's a stream of data that comes down to the clients. And, of course, we're, good reactive stream citizens, so at some point that set of messages will stop, right, because there's back pressure, right? And if we don't send another message saying, okay, send me some more, then, no more data will get sent. But if we do, then more data comes down. And of course, we can multiplex multiple requests over the same socket. Anyway, that's protocol stuff for another talk. Okay, so asynchronous streams of array. Those are I think, going to be key to the system. And I think having realized that, I think we're going to start. We haven't done all of this yet in Sparkle, but I think perhaps we will do it in more and more places, all the way through the system, really. Okay, asynchronous streams of arrays. I think that's the core data structure. And if you're working on something kind of like this, making processing, I'd love to collaborate with you. And if you're not working on something like this and you'd like to, well, me and my colleagues at Nest, maybe we'd like to hire you. Yeah, are there any? I think there's some Nest folks here already. Yeah, right. Yeah, there we go. Yeah, so go talk to those people. We'll give you a job afterwards. Okay, so now for the third section, I'm going to talk a little bit about architecture. So one of my colleagues, not one of the ones in the room, heard me waxing on about streams, probably, and said, what about this Lambda architecture? Yeah, you guys have heard of that. It's kind of these stream guys. What do I think of the Lambda architecture, right? So I went and read all about the Lambda architecture. And of course, part of it is great, right? Lambda. I mean, come on. Here we are in the functional program. I mean, so queries are pure functions, go on all the data. Totally on board with that. I think we all are. But the Lambda architecture isn't really about that idea. The Lambda architecture is about working around the fact that the batch systems we use for data processing, Hadoop here, is too slow. And so to solve that, what the Lambda architecture proposes is a dual pipeline approach. You're going to have a batch system, and in parallel, a streaming system, and then some query kind of coordination that's going to combine those two things. Right, and so so that's, and it's a reasonable solution to that problem. But maybe not the perfect solution. I want to talk about how we can perhaps make it a little better. So again, you got this problem, but the solution, the problem of having things, too slow. So we're going to make it fast by having two pipes. But now we have this problem that we have two pipes, right? And all the complexity that entails, both development-wise and operationally. But really, the thing I want to start by challenging is, well, are those really the only two options, right? We got the slow batch and the fast streaming. I think that there are other, this isn't the, my grandmother used to say the Sears catalog approach, right? If it's not in the Sears catalog, it doesn't exist. Well, are there really only two choices, streaming versus batch? In particular because we've been playing around with these systems that are high scale and low latency, right? I can show you how to put a dozen nodes in, the Google Cloud or the Amazon Cloud and, ingest 1 million items per second. I mean, that's pretty high scale and not that expensive, right? And you can process 1 million items in under a second, and really those numbers don't look too close to the limits yet. We see some optimizations that could make those quite a bit higher. So I want to introduce the idea of having what I'll call a live layer, right? A fast storage, high volume ingest, right? Connected with a fast computational layer, and furthermore that you can trigger the computational layer based on data being inserted, either with triggers or some other notification mechanism. Right. So, and of course, I'm interested in that idea because in the visualization in Sparkle, we're kind of building one of these things. So I think you could just squint at it, right? Sort of a live layer in the middle there. So okay, so how does this live layer fit in? We got a streaming layer, a batch thing, live. How's it kind of elbow into the picture? Well, I think the first thing to understand is that the live layer enables doing fast on-demand processing, right? You saw me zoom around in the graph. And if the data we're looking at is well aligned, you can do very fast processing. Right, and you can trigger it as data arrives, and you can do stuff interactively. What do I mean by storage grain? Basically, what I mean is, if the way that your database, your file system, whatever it is, makes it fast to read data out, right? The primary index, the way the data is laid out on disk, the columns laid out, however your database is organized, there's going to be one way to getting it out that's really fast. Right? And reading that way is going to be really good. Doing random reads all across the disk is going to be terrible. Right? That's going to be a major batch operation. That's not going to be fast. But I would note that writing against the grain, right? Writing against the grain is slower, but generally the systems are designed to make that feasible. It's an order of magnitude slower. Sure, it'd be better to write in stripes, but they're going to coalesce random writes into stripes internally. So you can actually write you sort of get a shuffle for free, right? The shuffles are the things that are expensive in the distributed system, data system like this, and you kind of get one, well, not free, but one inexpensive shuffle on the way into your data store. Okay, so how are we going to fit in our live layer, into the Lambda architecture? Well, the first idea is, the Lambda architecture calls for this kind of serving layer up front. We could buffer the data in the live layer, and then, I've showed you how you have a little protocol coming out of there. That can be the serving layer for our Lambda architecture. And really, that's a very reasonable thing to do. It's a reasonable place to begin. But let's keep going because, again, we never give up, right? We're going to keep trying to make this better. And my goal here is I want to kind of walk through the architectural possibilities and see if we can simplify the Lambda architecture and maybe improve some of the features we get. Right? So remember, we get this computational element now along with our live layer. right? So we could actually, rather than using this storage element as kind of a dumb, just serve up the data then to the people who, like an Apache server, right? We could actually do some of the aggregation, some of the math there, rather than perhaps doing it in the stream layer. Right, and there's some advantages to doing that. The obvious one is, history is fully available. We don't have to do the computation based on just a RAM window. A short RAM window. We can look at the whole history if we want. And of course, we don't have to calculate the aggregations, the whatever computations we're doing for the stuff that nobody ever looks at. Right? Usually in the streaming or the batch layer, what you're going to do is you're going to pre-calculate. You're going to set it up to calculate it for everything. But imagine we're using this to do a sort of graphite monitoring system of our server cluster, and we got 1,000 servers and 1,000 metrics, and we want to be able to provide visualizations on all of those metrics. Nobody's looking at most of them most of the time, right? It's only when you go and drill in that you actually need that data. So why do all the transformation in advance? So as a rule of thumb, anything we're doing that's grain aligned per entity, I think we could now do that transformation live. So here I kind of tried to show how the stream layer got a little smaller, right? Because we could offload some of that to the live layer. And the API for that, in the first part of the talk, we talked about how the API for coming off the disk was going to be one of these data streams. And the API for doing stuff that's triggered off data that comes later, well, that's going to be one of these data streams too. So that leads us to an API that looks something like this. This is kind of our read API. You say, I want this chunk of data. And if I want to get the ongoing data too, well, I can get both of those at once. Kind of logically, there's the part that comes off the disk, and then there's the new stuff that's added, at the end of that, and I just want both of those, right? And so I divide it here into two. You can, as a consumer of that, just concatenate the two, and that's quite reasonable. But it's sometimes convenient to know that which set is maybe you want to do windowing a little differently, or the protocol messages are going to be a little different. So the API starts to look similar for these things. Okay, so now back to our architecture story. So we're trying to simplify. Okay, we made the stream a little bit. So let's take a look at this ETL thing, right? Extract, transform, load. So what are we doing in this extract, transform, load? Usually, we're doing a couple of key things. Right, we're going to do format conversion. We got the data formats of the kind of the real world. And we're going to convert those into the data formats that are convenient for analysis. Right? But I'll note that we're doing that already, over here for the stream layer. Right? We're probably doing that already. And the other thing we're doing is we're doing this kind of grain realignment. We're going to denormalize the data from the however it comes at us in the world into however it's convenient for analysis. But I was just mentioning earlier how the live layer kind of is doing that too. So if we could take advantage, and we might be able to kind of replace this ETL layer with the stuff that we're already doing. Right? And that starts to look a little bit like this. Okay, so that's now we're starting to now we've gotten away largely already from the dual pipe problem, right? We're getting closer to a single pipe, right? And that's sort of the goal of this exercise. And I think if we do that, it not only makes simplifies the diagram, but I think it's going to really simplify our lives, right? Because we have fewer operational systems. We don't have to duplicate as much code in between the different layers. And operationally, it's going to be a lot simpler because we really are not duplicating as much. So, okay, so we talked about doing this live versus streaming trade-off. We can make the same sort of trade-off on the batch layer, right? Now, we have this computational element that can work on the live store. Which computations should we do in batch and which ones should we do live? Well, the nice thing about the ones that we can do live, right, is we can parameterize those based on the requests, based on the data we have at that moment. Right? You can turn the knob as a user, and that will change the parameterization, of the transformation. It's not based on the batch job we set up to run yesterday, right? It changes based on the zoom level or whatever it is you want. And in practice, if we deploy our transformations in this live layer, it's a lot more convenient operationally, because to deploy a new one, you don't have to reprocess all of history, which could take a long time, right? You just redeploy the new code, and maybe you're going to flush some caches. So again, that gives us the opportunity, I don't know if I showed it here, but I intended to maybe shrink that batch box a little bit by showing we could do some in the live. Okay, so once you get to a system like this, I think the implicit assumption of the Lambda architecture was, well, you know, slow is batch and fast is streaming. Okay, so what I think the implicit assumption of this architecture is, you know, for the ETL side, do streaming, right? If you want to do use the live layer to do the fast stuff with it, that's kind of with the grain, and use the batch layer to use the slow stuff that's against the grain. Right? And you know, that really covers the majority case. There may still be some more complicated scenarios where we really do want to do these very complicated and very live problems, and then we're going to have to build something more complicated out of the streaming or the live system or some combination thereof. Right? But we don't have to just do it if it's just because we want it fast, do it in the streaming layer. I think that was a false assumption of the Lambda architecture. Okay, so we got the single pipe touch batch. And I want to go one step further and talk about the data pipeline of the future, right? Because this is really what I was, you know, in at least this spiel for today, right? I was trying to get down from this 2-pipe down to 1-pipe, right? And I think this is actually going to become possible, right? As the storage layers get more and more capable of doing both low latency and high volume, I think we can get to a system a lot more like this. And of course, it's my view that that system is going to have asynchronous arrays all the way through. Okay, so that's the end of the architectural spiel. Let me just give you one or two quick demos. There's one more thing I wanted to show you. Okay, so I'm going to pop, so the other way you can launch some of this, play with some of this visualization stuff, is you can do it from the Scala console. Okay, so I'm just not going to quite type this stuff in all live. So here I just made a little Scala collection, right, with sign in it, right, and I'm going to make a couple more just for fun. Okay, so then if I have a collection lying around and I just pop into the console, then oh, that wasn't the button I meant to press. Okay, so there's my sign plot, right? And hello. And through the magic of you know, WebSockets, you know, it all just updates live, right? Because we got this streaming protocol with live WebSockets, and of course this is all live again and zoomy. Okay, so I wanted to show you that you could play with the console, but really that was the setup for this this next bit, right? I've talked about, well, you know, could we combine the idea of having these a live store with some kind of a batch store? You know, and if only there were a way to run these kind of batch operations in Scala, you know, how would we do that? You guys see what I'm typing? Right, so if we just had Spark, and you know, Lambda architecture, right? It's all about you know, functions on all data, right? So if we had a little Spark layer, that could get us an RDD, right, of, let's say, all the data that we've been using in this demo, right? So here's all the names of the columns, right? And let's say we want to run some cross-grain, potentially difficult query, right? Here, let's go grab all the data for all these P99s we've been looking at, right? And here, what we get back is an RDD of data arrays. Right? So just like we were talking about before, so this is kind of hinting at how you can unify some of the batch operations with some of the streaming operations, right? It's the same data arrays underneath. So I think that's my main point. But just to kind of see it all the way through, we'll go find the P99s. We'll see which ones lasted longer than a second, and then we'll go execute the actual result in Spark. Collect the results and then plot them. Okay, so there you can start to see how both how the big data solutions can start to get merged with these live solutions, and also how Sparkle is starting to get useful for not just the small data problems, but also these bigger data problems. Okay, so I hope you've seen, just wrapping up now, I hope you've seen how Sparkle is kind of a useful tool, and more importantly, some of the lessons we've learned from Sparkle I hope can be useful for some of the things you might try to do in building data pipelines for other purposes as well. Thank you very much. So I think, how are we doing on? Yeah, so you want to do some questions now? Okay. And if not, we can do some questions after just find me afterwards. Go ahead.
I was right with you until you started talking about P99s lasting for longer than a second. What's P99?
Oh, yes. So P99 is the 99th percentile. So what this data was from, if I remember correctly, we were looking at a database, this is some old data, looking at some performance issue we had, but I think it was actually a SQL database that was under a lot of strain. And the time to respond, the 99th percentile time started to get to be really long. Yep. I think the average is starting to get bad too, but the P99 is sort of your early indicator of trouble. Yeah, go ahead, Bob.
Comparing this, this reminded me of better way to pattern the Blue. So comparing this to what Heather suggested about passing the lambdas as close to the data as possible.
Yes.
So how would you compare these solutions?
I think that's a really good idea. In a sense, that's I think that's very consistent with this principle, right? In that, what we tried to do in the first stage was we tried to move some of the computation out of the visualization client and move it up to the cloud, right? So then the question is, how close can you get that computation to the magnetic media where the data is, right? And what I've suggested here is, if you, I won't flip back to that slide, but it's kind of a separate. You got your disk, and then you got your computational. Those are sort of separate servers, right? And if we could move those a little closer, that's a win. I think that's a great idea. Yeah. Yeah, and as to whether to have the flexibility of sending up individual, sort of custom composing a Lambda, I think that also is very interesting. Right now, the extension model is that it should be very easy to construct a new transformation, but to install that new transformation, you have to recompile. And being able to deliver one without recompiling would be quite nice. Yeah, so lambdas would be cool. Spore lambda delivered would be cool.
Go
Go ahead.
So that
Yeah, I would be interested to talk to somebody about that, but no, there hasn't yet. But yeah, I think part of the goal in showing this off is to sort of flush out some more opportunities for collaborations like that. Go ahead. Thank you.
What is the biggest update from the point of the last year's Scala?
Yes. I've been not the greatest at keeping the repository up to date, but it is reasonably up to date now, and I think at some point we can start naming the releases. I think we're on about 0.5, and we're probably due to declare a 0.6 sometime soon. Okay, I think we're about out of time. Thank you very much. Any more questions, please come find me. Thank you.